In this short video, we'll introduce some important vocabulary and we'll build on the idea that the scientist himself or herself dictates how energy manifests. Energy doesn't care. So the vocab first, we have isobaric. Isobaric conditions can be imposed by the scientist and they mean that the change in pressure is zero. Isobaric conditions exist in the lab when nothing is sealed and everything is just open to the lab atmosphere. So that would be isobaric conditions. Isochoric conditions are when the change in volume of a system is zero. This would be when a system is sealed with a rigid container so that the container won't expand or contract and, for example, a gas couldn't get in or out. Isothermal conditions are when the temperature change is zero. So when you have a water bath as a sink or a source of heat energy. And adiabatic conditions are when change in heat is zero. So when changes are rapid and heat doesn't have a chance to adjust, so typically rapidly changing conditions can be adiabatic. We're going to focus on isobaric conditions for now. So let's take this equation H. Well, let's start with what we saw in a previous video. Delta U is Q plus W. So we said that change in internal energy is heat and work. And we know this is the first law of thermodynamics. Okay. We've already said that how energy chooses to appear or manifest itself depends on the opportunity presented to it by whoever designed the experiment. You allow it to do work, don't be surprised when you see work. You allow it to show heat, don't be surprised when you see heat. There's also another equation that's very similar, and that is H is U plus PV. So these are both fundamental equations that I would commit to memory. That would be my suggestion. H is called enthalpy. We've seen U before, it's internal energy. P is pressure. And V is volume. So H is U plus PV. So let's look at change in enthalpy. So here we had change in U, so let's look at changes in these variables. So a change in enthalpy should be a change in internal energy plus a change in the product pressure volume. Okay, just check and make sure I press record. Okay, a change in enthalpy is a change in internal energy plus the change in the product pressure volume. Now, the change when it hits a product, we have to follow a rule called the product rule. So the change ignores pressure and only hits the volume, and then the change ignores volume and only affects pressure. So the change of this product, we ignore product, so write P, then the change hits the volume, and then we ignore V, and the change hits the pressure. Okay, so that's how we apply the change to a product. So let's rewrite this. Change in enthalpy is change in internal energy plus P change in volume plus V change in pressure. Okay, so we have a longer equation. we can take all of this stuff to the other side if we want to. So we can say change in internal energy is change in enthalpy. So I'm going to take this stuff to the other side of the equal sign. So change in internal energy is change in enthalpy minus pressure delta V minus volume delta P. Okay. Now, if I compare that with my initial equation, if I compare that with the First Law of Thermodynamics, I had delta U is Q plus W. Now W, we'll put it here, work, the way we think of work, or a way that we can think of work, is minus P delta V. So this is work as pressure delta V. This is known as expansion work. So what would do expansion work? Imagine gas inside a cylinder and you ignite it and it pushes the cylinder up, or a piston. That would expand against the obstacle of the piston. So anytime something expands, that would do work. The negative sign here is a definition. It's not a real negative sign. It just means a loss of energy. If work has units of energy, this system has lost energy. So that's the meaning behind this negative symbol here. So instead of work here, I can replace work with negative P delta V. So we notice that this part of the equation looks the same. It's suggesting that delta H and Q are equal, which is interesting. But I can't just ignore the V delta P unless I can make this equal to 0. So V delta P equals 0 whenever delta P is 0. Well, delta P is 0 under isobaric conditions. So if I impose isobaric conditions, then I force this term to disappear. So we've learned that under, and this is a very important point, under isobaric conditions, heat equals change in enthalpy. So something with a lower symbol, or Q, is equal to something with a capital symbol, delta H. This is very important, and we'll extrapolate this a little bit in a final video.